Hello and welcome to AIM Solder's next edition of Ask AIM. We want to bring our support and expertise to you, the customer. I have Tim O'Neill, the Director of Product Management for AIM Solder, here answering questions today. It seems that low temperature soldering alloys have become a hot topic within the SMT industry. Our first question asks, what is low temperature soldering?
Hey Logan, I see what you did there. Low temperature is a hot topic, but it's true. It's getting a lot of play in the industry right now, and I have participated in multiple webinars and presented multiple presentations on considering and adopting a low temperature. And I think the first question is the one you just posed. Well, what is low temperature? It seems as though there are two categories of low temperature. There's reduced temperature and there is low temperature. And reduced temperature is roughly defined or loosely defined as peak reflow temperatures below 190 degrees Celsius. And low temperature is peak reflow temperatures below 170 degrees Celsius. So there's two classes of alloys that have evolved. True low temperature alloys are close to the tin bismuth eutectic of 42% tin, 58% bismuth. When you get away from the tin bismuth eutectic by either dropping the percentage of bismuth relative to the amount of tin or adding additional elements in order to compensate for some of the alloy characteristics of the tin bismuth eutectic, the melting temperature will tend to rise. So increasing melting temperature gives us the second class of alloys that are somewhere between 170 peak reflow temperature and 190 peak reflow temperature. So depending upon the application's requirements, you can look at these different alloy offerings and decide which one meets the mission profile of the assembly. So in effect, that is what low temp is.
Our next question asks, what are the advantages and disadvantages of using low temperature solder materials?
So low temperature solder materials, as defined as materials that reflow below the SAC 305, peak reflow temperature requirements for that material are around 245 C. You can get away with 230, 235, but typically people target 240, 245 C. That's quite hot, and it was one of the biggest issues in transitioning from a leaded tin lead system, which had peak reflow temperature requirements under 220 C, to this 240 to 245 C required peak temperature. Plastics deformed, laminates delaminated, and the excess temperature just was very hard on the materials. You know, I've heard it said that the harshest environment any circuit board withstands is the assembly process. And I think that's a great thing to keep in mind. So by lowering the process temperatures, we can reduce the amount of thermal exposure of the assembly, which has some significant advantages. The most significant, and it correlates with what's happening with the electronics assembly market in general, is that as circuit boards become thinner, smaller, lighter, and more capable, they are more prone to deformation during the reflow process. So a very thin substrate and a very thin component, when exposed to SAC 305 soldering temperatures, will tend to deform or warp, which leads to soldering defects. So that's the main driver for the exploration into low temperature materials or reduced reflow soldering materials. Now, these materials have other properties that are somewhat less desirable than the SAC 305 that's currently in use. And those have to be taken into consideration when determining if a low temperature process is appropriate for the product. So the most concerning of the low temperature alloy properties are the brittleness that's imparted when bismuth is part of the alloy system. And bismuth is pretty much used in all of these low temperature materials in some degree. So it's a tin bismuth plus system. And those systems are very brittle as a result of the bismuth content. We can decrease the bismuth content to try and reduce the brittleness or improve ductility. And then the flip side of that is as I start to raise the melting temperature, and that's where the balancing act takes place. From what I can see, AIM and our competitors are working diligently to come up with an alloy that is the best compromise between these two worlds, a low temperature, low peak reflow temperature, and a sufficiently mechanically strong solder joint. No one material has emerged as having the optimal properties, and it seems unlikely to me that there is going to be one solution to all of it. I think it'll be reduced down to a couple of options that people are comfortable implementing. And as our experience and exposure to these materials, their in-process performance, meaning how easily are they used in the production process, and then their reliability characteristics in the field will determine what alloys would be the most suitable for a given application.
Our last question asks, how do I implement low temperature solder materials into my process?
Well, the good news is, Logan, is that it probably shouldn't cost too much to at least experiment, and if you decide to go forward, to implement. The first thing that I would do is I would recommend making sure that none of the materials that are currently in use contain lead. It's very important that a low temperature solder not make contact with lead, as a three-part alloy is formed with the bismuth and tin that has a melting temperature of 97°C, which causes a significant loss of reliability. So that's step one, and shouldn't be a problem for most of the industry. There are still some legacies out there where we see tin lead in use, but they're becoming less and less common. We won't have the capital investment that we had when we transitioned from leaded solder to lead-free solder. All of the equipment that's lead-free capable is also low temperature capable. When we transitioned from leaded to lead-free, new ovens had to be purchased in order to accommodate the higher peak reflow temperatures. New wave solder equipment had to be purchased to accommodate the degradation of the innards of the equipment by virtue of contact with the molten lead-free material. And so those things won't have to take place. The biggest issues will probably do with customer expectations and process adjustments. So for example, the aesthetics of the low temperature material will be different than the material that is currently in use. The residues can look different. So there are those accommodations that need to be considered. There are other things that we're still discovering as low temperature solders get more widely implemented. I expect that the low temperature solders will probably have some sort of aperture modification that will have to take place in order to accommodate the different flow and spread characteristics. They tend to be fairly sluggish wetters. But on the other hand, something we've discovered is that they also tend to be very low voiding. So that's a big benefit. So aside from the reduced warpage, we may also see lower voiding on bottom terminated devices. Lower voiding, less head and pillow defects, which is the driver in most cases for this. You know, the low temperature revolution is going to take place at surface mount first, and then may find its way into wave soldering. One of the interesting things about low temperature materials being primarily high bismuth materials is that bismuth is like liquid water in that when it freezes, it becomes less dense as a solid, like an ice cube floats in a drink as a solid. And in most materials, the solid is more dense than the liquid and sinks. Bismuth and water share that in common. So we'll have to take into consideration the effect of that on the equipment. There may be some solder pots that have to be reconfigured or redesigned or incompatible with that characteristic of high bismuth materials when used in wave soldering. But the advantages to a wave soldering process are considerably less than the advantages in a surface mount process, because the main driver here is reduced component warpage, reduced substrate warpage. Going to a low temperature material in wave could reduce your energy costs. So I'm sure that's why people will investigate it for those applications. But by and large, it's a drop-in. You could conceivably start testing it today with the existing materials and learn some of the tricks that are going to be required for trouble-free implementation. But I'm fairly confident with a good solder vendor partnering with you to help you understand what those problems are and what the solutions may be. This could be a very successful endeavor and yield positive outcomes.
I hope this gives you a quick summary of low temperature solder materials and how they can be implemented in your process. If you have more interest in exploring the use of low temperature solder materials, AIM tech and sales support, along with AIM's website, aimsolder.com, are available as a guide in your education using these materials.